So we're going to talk about troubleshooting. Part of that is just a very brief overview of IPsec itself. IPsec is, as you all know, I'm sure, is a way of doing site-to-site data center connections between partners who are not one organization, or there's not a complete trust profile. So you want to set in place, number one, you want to have encryption over the internet. And then you also want to set in place policies that limits what you will show from your network and limits what you will see from their network. This is done, two key elements of it is the first part of the communication, which is called Internet Key Exchange, is done over UDP 500, UDP port 500. So obviously that has an impact on your security groups, and we went over security group best practice at the last session. And then depending upon whether you're going to use what's called NAT-Traversal, which means that one or more of the IPsec devices appears to be behind a gateway. It's not an internet edge device. You then would use what's called NAT-Traversal, and that is basically the IPsec protocol encapsulated inside of UDP port 4500. Or you could be using native IPsec, which is its own protocol. So it's not port 50, it's protocol 50. The name of the protocol is ESP. So ESP sits on top of the IP stack, so it's comparable to TCP or UDP. It's its own protocol, ESP. So IPsec with VNS cubed, here's some high-level things. We do what's called a policy-based VPN. And that effectively is what I just spoke about, which is that you offer something from your network, so a subnet or set of subnets, and then you ask for something. So you're wanting one or more subnets from the customer from the other side, and by defining that set of to-from relationships, you're implicitly putting in place firewall policies and routing policies to connect those two subnets together. And again, in the case of policy-based VPN, it's done implicitly by when you say new tunnel on the VNS Cube device and you put in that from to pair, what's happening is you're creating effectively a firewall policy and a routing policy all in one. It's becoming very popular. Some of the devices are now supporting what's called a route-based VPN. And effectively, that's opening up the two networks to each other such that anything from anywhere to anywhere can flow. What that does is it makes it easier to get the basic connection up and running because there's no constraints. It just I'll accept any traffic from your network and I'll send any traffic to your network. But then it requires explicit creation of then some routing policies and some firewall policies. We already mentioned ESP. ESP is the protocol. There is a way of doing IPsec with what's called authentication header, AH. It's effectively not used. It's not secure, and we don't support it. Same thing with tunnel mode versus transport mode. We use tunnel mode. Transport mode is not as secure, and we don't support that. IKE we already talked about. That's what's commonly used for phase one setup. There really isn't there isn't much else done. Then there's a mode called main mode versus aggressive mode. Again, from sort of earlier days of IPsec, there's a mode called aggressive mode. All it does is it does the initial communication, sort of that phase one communication more quickly. We're talking something that takes milliseconds to do anyway. But in aggressive mode, again, less secure. So we don't support that. And then you can authenticate between the two devices using a pre-shared key, effectively a shared password, or you can use X509 certificates. Using certificates for authentication between the devices generally works between vendors of the same style. Generally is hard to make work from an interoperability point of view. So for interoperability, what you'll find is everyone uses PSK still, and we don't support certificates. So we don't do route-based. We don't use authentication header. We use tunnel mode. We don't use transport mode. We use main mode. We don't use aggressive mode. And we don't use certificates. We use pre-shared key. For those of you who've worked on a number of these tunnels, you know, a request for authentication header or transport mode or aggressive mode, I'd be surprised if you've had more than one or two of those requests because they're just not common. They're sort of part of the legacy of IPsec. Let's look at the key parameters. The key to troubleshooting is getting it right in the first place. There's something around 14 parameters that you need for a stable IPsec site-to-site VPN connection. And if you match those exactly, you're going to have a successful connection. If you don't, there's something wrong with security groups on your Amazon side, or there's something wrong with the ACL on their side. From a VNS3 point of view, we talk about endpoint IP addresses. That's the public IPs of your VNS3 and the public IP of whatever the customers or connecting parties IPsec device is. Then phase 1 and phase 2 parameters, they have to match to have a stable connection. You can sometimes get a connection when they mismatch, but what you'll find is you'll end up out of sync, and after the initial rekey period, or you know, after some period of time, you'll see that they get out of sync with each other. There's some parameters that don't have to match and you don't have to use. One of those is dead peer detection. That basically is a fallback for your device. When the counterparty's device has died, it basically puts your device in a mode where it's trying to connect, realizes it can't even see the device at its public IP, and effectively resets itself to try again to connect to it. It's just a part of sort of automated failback where you keep trying properly to connect so that when the other device does recover, your connection resumes. And then there are some compatibility parameters for unusual situations. If you're connecting to partner A and partner B, your connection for partner A needs to match what partner A has, and your connection for partner B has to match for what partner B has. You can have different things for partner A and partner B. So phase 1 parameters are NAT-Traversal enabled or not, and we'll go into detail on each of these. The pre-shared key for authenticating between the two devices, basically a shared password. What's called the IKE Internet Key Exchange Peer ID, which is often not used. Phase 1 algorithm, phase 1 hash, phase 1 Diffie Hellman group, which has to do with how key exchange happens, and the phase 1 lifetime. All of the connections to a given VNS3 have to either be native IPsec or NAT-Traversal. If in the case it might be a customer, multiple data centers connecting in cloud with different networking teams, and one of them wants to use NAT-T, one of them wants to use native IPsec. As I mentioned, the initial negotiations occur on UDP 500, and then really the only difference between these is NAT-Traversal causes the IPsec protocol to be encapsulated in UDP 4500 because the connection isn't on the internet edge, and lots of network gateways can't protocol forward. They can port forward, but they can't protocol forward, so you have to encapsulate the IPsec traffic. If the device you're communicating to is on the internet edge or is behind a device that can do protocol forwarding, you can use native IPsec, and then that uses protocol 50 again. It's not port 50, and you'll see it if you've ever set up the Amazon VPC security groups. The security groups, you can have UDP rules, custom UDP rule, custom TCP rule, and then you can also pick custom protocol rule. So one thing that's important to remember is NAT-Traversal has NAT in the name. It doesn't really have anything to do with NATing your application traffic. It just specifies whether the communication between the two devices on the outer edge are going to go via UDP 4500 or protocol 50. Pre-shared key. So this is the easiest form of interoperability. It's for authentication between the two devices. It's effectively a shared secret. So if you think about it, you set up your VNS3, you set up your security groups, and we covered in the best practice guide, if the partner you're connecting to, let's say, is their device is at a public IP of 66.66.66.66, you should set up the security group to say, I'll accept UDP 500 and either UDP 4500 or protocol 50 from 66.66.66. and he should do the same on his device. He should only allow that protocol from you. So that basically takes care of most of the sort of security concerns. But you want to be able to have a pre-shared secret to differentiate between different connections, and that's what's called pre-shared key. It needs to be identical on both sides. The number one reason for pre-shared key issues is copy-paste. If you're going to use copy-paste, you need to be using a absolutely plain text editor that does not support any formatting characters, any invisible characters. Today, in most implementations, we're starting to see the standard does support effectively your side to have one secret and the other guy's side to have another secret. So you effectively would have, kind of think of it as if the cloud is up and to the left and the data center is down and to the right, effectively a left PSK and a right PSK. The Internet Key Exchange Peer ID, or IKE Peer ID. We have this concept of local private IP. What this is this is two things. Local private IP is the private IP used by NAT-Traversal. So some boxes, an example is a Watchguard Firebox. The Watchguard Firebox has to know the IP address of the device that it's connecting to, not only the public IP, but the private IP. So if you brought up a new VNS cubed, and so the WatchGuard has to be configured with our local private IP. If instead of our local private IP, you were configuring the WatchGuard with the actual private IP of the VNS cubed, the next time you brought up a VNS cubed for this topology, if you have to migrate or Amazon killed your instance or something, if you didn't bring it up on this exact address, the partner would have to edit their configuration, right? Which could be catastrophic. So what the local private IP is it's a persistent private address that regardless of what VPC address you have, it's what the other side can be told to use for that setting on their side. So it's a way to give you better configurability without any changes to the configuration in the event of a change. Where you see this on VNS cubed is you see the local private IP address. So that's what local private IP does in part. We also use the local private IP as the IKE Peer ID. The customer will sometimes want to know what your remote peer ID is. From their point of view, you're remote. From your point of view, they're remote. So you need to know from which point of view you're talking about. So on boxes, some boxes, I think you'll see this in the Juniper document. You'll see on their web UI it says local peer ID, which from the customer side, the Juniper side is its side, and remote peer ID, that's you. So what will happen is when somebody needs that local private IP for the configuration to work, they're going to put it in their device under the setting called remote peer ID. So the key, most times this isn't explicitly needed, but I know, for example, WatchGuard Firebox it is, and we run into that occasionally. It is needed for VNS cubed to VNS cubed connections, actually, and I'll show you that in a moment. Phase 1 algorithm basically is just the encryption algorithm that's going to be used in the Phase 1 communication. Sometimes people will call it IPsec KMP. Sometimes they call it IKE. There's basically very limited choices. Your choices are AES 256, AES 128, and 3 DES. And this comes out in the section in extra params where the extra parameters box where you'll specify Phase 1 equals. The other part of the Phase 1 communication is the hash. And this is a hash function that's used as part of the encrypted communication. So the more newer boxes and more newer connections, people might be asking for SHA-2 as opposed to what was, sort of these are in order of security. MD5 is not used really hardly at all today. You'll run into that with an older box. You'll have a customer who has an out-of-life, end-of-life box, and they're going to ask you for 3 DES MD5, and then we'll see the Diffie Hellman's DH2. And that's was state of the art probably when that box was made, but they haven't been able to upgrade it. 75 is not used very often. SHA-1 is what most people use today, but people are starting to move to SHA-2, and SHA-2 comes in two flavors, 256 and 512. And so there you need VNS Cube 35113, which is what we're giving you when you set up new instances today. So it has to be 35113 and above to have access to that. Phase 1 Diffie Hellman, again in order of security. There is an 18 that some people are using now. We're seeing a move to 14, but most of your connections are going to be 5. And these literally just represent, each of these represents actually a byte specification of how the algorithm and the computation is done. And then phase 1 lifetime. Phase 1 lifetime is most commonly done in seconds. It's every now and then somebody will say 8 hours or 24 hours, but they usually give you a large number, and that's in seconds. You have to match what the customer has to have a stable connection. So we will take, VNS3 takes the first thing that the other side offers. So whatever they offer, we'll agree to. We don't push our own thing on them. We say whatever you tell us first. So what you want to have in extra params box is matched to whatever it is they're asking you for first. So they tend to be 3,600 seconds, 28,800 seconds, and 86,400 seconds. So 1 hour, 8 hours, and 24 hours. There's no rule that you couldn't use a different number of seconds. It's just not commonly done, and there's probably some boxes who would fail if it's not one of these functions that as you talk to them. Phase 2 parameters are effectively the same, slightly different in how it's done. Phase 2 doesn't use a Diffie-Hellman group, but phase 2 can be negotiated with what's called perfect forward secrecy. So you have an algorithm, you have a hash function, and then you have is perfect forward secrecy on or not. And then you have, if PFS is used, then there is a Diffie-Hellman key exchange as part of PFS, so you need to provide that. Then your phase 2 lifetime, and then effectively the set of parameters, which is subnets offered and subnets requested. And we do that via tunnel pairs when we set up VNS cubed. Phase 2 algorithm is sometimes people will talk about what are you doing for IPsec or what are you doing for ESP. Phase 2 algorithm, again, is the encryption algorithm used, and the same choices are available, AES 256, AES 128, and 3 DES in order of security. The hashes are the same in order of security. The most commonly used is SHA-1. It's generally end-of-life equipment that uses MD5, and you'll start to have people asking you for SHA-2 is becoming more popular. Perfect forward secrecy is a on or off thing. Both sides have to agree. If you have PFS on and they have PFS off, we have seen it negotiate and connect, but then we see never-ending problems. So you won't have a stable connection. Both sides need to agree, and then you need to agree whether you're using one of these groups. 2 is still very common. 5 has sort of been recently the gold standard, but as there's been more concern about the ability to decrypt traffic, people are moving to 14 and 18. Phase 2 lifetime, same thing. Common lifetimes are 3,600, 28.8, and 86,400. The key there is that they can't be the same for the same connection. Same rules apply. Then there's a few optional things. We talked about dead peer detection. So as a rule, it's a good practice to have dead peer detection. Every now and then we have had cases where the connecting party has had to keep DPD off because there's something about the way it was sending it that was causing a problem for VNS cubed. And I think we've occasionally had the same. But general rule of thumb would be get your connection up and running, make sure it's stable, makes it through phase 1, rekey a couple times, makes it through phase 2, rekey a couple times. Everything seems good, and then add for better recovery capabilities, add the DPD parameters thereafter. And then I mentioned, again, there are parameters that stipulate aggressive or main mode where effectively let's call it hard-coded to main mode or hard-coded to ESP, non-authentication header, We're hard-coded effectively to tunnel, not transport mode, and we use PSK. Let's look at the configuration process, and I'll show you some screenshots, and then I'll also go through it live. So in this documentation, we basically will show the key steps. These are all things that are in the configuration guide. What I'll do here is I'm just orienting you. This documentation shows you about the IPsec page itself. The local private IP we talked about, which is a persistent NAT-Traversal IP, but it's also your IKE Peer ID. And that's what that means. And then logging link is there on the IPsec page where you can see the IPsec log file. Again, another to-do for this year is to add a logging page so you can see, today's log, yesterday's logs, etc. More easily. There is a verbose logging there. Please don't turn that on unless you're working with us and we've asked you to do that. Ultimately, it will be days, it will be weeks, but you will fill up the hard drive of the VNS cubed and then it will be hung. So verbose logging is really there just when you're working with cohesive. So then on that page, the IPsec page, there's a define new endpoint function. So when you click on define new endpoint, you put in the name of the connection, you put in the public IP, you put in the public IP of the device you're connecting to, you put in the pre-shared key and you validate it. It effectively acts almost like a page password. You have to know what it's set to in order to save. If the other side is behind a NAT and you need to know its NAT address and its peer ID, you put it there. Enable PFS is toggle on or off. GRE tunnels are very rare. And then basically the extra params box where you can stipulate specifically your phase 1 policies, etc. And I'll show this on the larger screen in just one moment. So here's some notes, and again, this is from the configuration guide. VNS Cube can do auto discovery of what the other customer is doing. Once you've sort everything out, even though it's called extra params, put in as specific as you can a match to what the customer is doing. Right, so phase 1, so things could be like phase 1 equals AES 128 SHA-1. You probably want to put in the Diffie Hellman group as well. So you want something like AES 256 SHA-2512 DH5. You want to specify the algorithm, the hash, and the Diffie Hellman. Same thing with phase 2. Specify your algorithm, specify your hash. PFS group is PFS group equals something like same sort of thing. DH2, DH5, DH14, DH18. Your lifetimes, S for seconds. The default settings on VNS cubed are 3600 and 28.8. But again, be specific to match what the customer is doing. And then, as I said, once you've got a stable connection, you've been through multiple phase 1 rekeys as their lifetime expires, multiple phase 2, then what you would want to put in for greater recovery is capability is DPD action equals restart. And then DPD delay means how long you'll wait. This is basically a heartbeating function. It sends hello, are you there messages. And as long as the other side answers, everything's fine. The delay is how long to wait for an answer to come back. And the answer is 30 seconds. And then effectively, if no answers come back in 30 seconds, you'll do another one. If no answer comes back in 30 seconds, you'll do another one, depending upon your timeout. So in this case, with a timeout of 90 seconds, we would basically attempt to say, hi, are you there? And after not getting a response to 3 different hi, are you there inquiries, 90 seconds later, we would reset the connection and try and start everything over again. There's some less common things. By default, connection is bidirectional. What that means is we'll attempt phase 1 negotiation with them. We'll initiate it, and we'll also are willing to listen to them initiating. So we'll accept a phase 1 negotiation from them. We'll also initiate a phase 1 negotiation from them. If for some reason we wanted to be passive to them, where we don't ever initiate to them, they'll initiate to us, and every now and then, again, talking to an old box, we might have to do this. The other option is receive. And then should we rekey or not? Should we effectively say, hey, I'm expiring the phase 1 or phase 2 key set, let's do it now and agree on what the new key set are. Again, we've run into older boxes where we have to put in connection rekey equals no, where we just let the other box drive everything because we'll appropriately respond to their requests for key events, but they'll effectively be ignoring our requests for key events. So this is pretty rare. And then sometimes there's some subsystem parameters that are understandable by our IPsec subsystem, but we don't use them often and we don't recommend them. And there's a syntax called compatibility. Compat and then some colon and then some text. And again, usually those are something you would use with cohesive while we're working together to solve a connection issue. Once we put in the endpoint, the option on the screen is then you can edit the endpoint, you can delete the endpoint, you can put in a new tunnel, and if you're doing a type of IPsec connection called BGP peering, you can create an eBGP peer. To date, none of Pega's customers, as best I know, are using BGP peering. We're starting to see a resurgence of BGP peering in our customer base, so we're actually in the process of refactoring the user interface and how that works and making that more flexible. But ordinarily what you're doing is a new tunnel. And then the tunnel specification is the last part really of this phase 2 connection, where you're saying, I will offer up the overlay, in your case, and I want from your side, I want you to give me access to a subnet. At that point, let's look at what this would look like in sort of real life. So here, I've got a VNS3 controller. My local private IP is 192.0.22.54, and I haven't made any endpoints. So as I said, one of the key things to do, so let's pretend I've got my guy and he's given me the things he wants, right? So he's told me his public IP, he's told me his remote peer, his IKE Peer ID, he's told me what the pre-shared key is, and he's told me what he wants for phase 1, phase 2 deployments. He's told me what subnets he's offering, and he's telling me what subnets he wants. So I'm just going to move this off screen for the moment so I can copy paste more easily. Making an endpoint on VNS3 is pretty easy. We put in a human readable name. I'm going to go to test controller 2A. We put in the public IP of that device. We put in the pre-shared key. To the degree it's not something untypable, we don't use copy paste for that. In this case, I need his IKE Peer ID because VNS3 to VNS3 using NAT-Traversal does require that. So I put that in. I'm going to use perfect forward secrecy. So that's a toggle on off. I'm using PFS. GRE is a very rare element. So I've said I want phase 1, AES 256, my algorithm, SHA-1 my hash, DH5 my Diffie Hellman key exchange group. Then for phase 2, I want to use AES 256 SHA-1 is what the partner told me. So again, same thing, very easy, the algorithm and the hash. PFS is on, as you saw above. PFS is on, so we should match on our PFS group setting. So PFS group equals DH5. Phase 1 lifetime, we're using the VNS3 defaults here, but again, be specific as possible to match with your customer. And then create. Now you'll notice again, I'm not putting in dead peer detection parameters because what we should do is we should make sure that everything's working, and then we go to then we should add in greater reliability features. So hit create. At this point, nothing happens in terms of communicating to the other side because we haven't specified any policies of what we want from them or what we're willing to give them. So for now, you would not see any traffic going if you went to the network sniffer, right? Because we're talking to this guy. If if they've set up their side, we might see some traffic coming from them. So let's go in. So the network sniffer is an important thing to know. So let's, we'll go in and we'll say source of their thing or destination of their thing. And we'll start a dump. We might be seeing some requests from them, or they may not have set up yet. So then we'll go back to our IPsec. We'll say new tunnel. And so I'm going to offer up my overlay, which in this case is it prompts me here, tells me absent anything else, use the overlay CIDR. And then what I want from him is I want his subnet 172.30.103.0.24. And I hit create. And then now I should start to see some negotiation traffic going between the two sides with at least me asking for connection. I can go back to my network sniffer. And I see from my device, I'm trading some identity messages with them. But so far maybe haven't gone beyond that. So let me go back to my... And then while we were off looking at the network sniffer, what happened is phase 1 and phase 2 completed, and we now have a connection. So what this page shows is I refresh. What refresh will show, if you click refresh, you'll see the counters counting down. So you'll have seen the lifetime remaining counters count down. We don't do that live on the page. You hit refresh on the connection. Restarting the connection resets the tunnel and will disrupt traffic momentarily, so you don't want to do that unless that's the objective. Delete, also obviously very bad. You don't want to delete the tunnel. So unless it's something that you're out to do. These are editable now. They used to not be editable. So if for some reason the guy on the other side had told you wrong and this needed to be a /22 or /25, you can just come and cancel it. Edit it. You don't need to delete the entire tunnel. And then you can see a subset of the logs. So what we see, so what this is there's a log file. The data above the line is the latest information from the overall log file. The log file has information about all your connections, all the rows are all interspersed together as different information comes in. Above this line is the latest information from the log file. Below this line is information from the IPsec runtime. So what we see is that we offered up our 192.168.203. We asked for their 172, so we see that that's what the sort of requests were. We see what we asked for, so there's a variety of runtime information in here. And then the key things to see is we see that we have a phase 1, IPsec AMP, as I said, sometimes it's called. And we have a phase 2, we have an IPsec SA. So, and we see the counters counting down as well, right? So all of this information that's in here is summarized. So this is the detail. And there's a refresh button. So if you hit refresh, we go get the latest log information. We get the latest runtime information. What will have changed is those counters. So this is the sort of detailed view of what you're seeing on this page. We're showing the same things. So we do, if we do a refresh here, we see that we have the tunnel type IPsec. Our phase 1 is established. We're using AS256 as our encryption algorithm. We're using SHA-1 as our hash. Diffie Hellman key exchange 5. The lifetime is counting down. Phase 1 lifetime has this much left. Our phase 2 or IPsec SA is established. Again, phase 2 encryption, phase 2 hash. We're counting down from 28.8. SPI stands for Security Parameter Index, and that's just kind of how the network world works. The name that they named it in the code effectively is the name that survives up into the world. So what a security parameter index is this is a hash key in the implementation of IPsec where you go look up the outbound part of your tunnel for communicating to the other side, or you look up via the inbound SPI for the inbound side of the tunnel from the other side. So these, when you're debugging with the partner, these change when your keys refresh, right? So when your phase 2, if your phase 2 is refreshed, then you'll have new SPIs. So we'll get new SPIs in just under 8 hours if this is a stable connection. So this is a critical part of debugging with the other side when they say, well, I'm not getting any traffic from you after you've exhausted ACLs. You start saying, well, maybe you're holding on. Maybe when we negotiated, you created a different set of indices to your tunnel elements. Perfect forward secrecy is enabled. Perfect forward secrecy, Diffie Hellman, NAT-Traversal is on. We put on dead peer detection by default when we're talking between VNS cubed to VNS cubed. I mean, that's the essence of that tunnel. What we call tunnels, right? Other people will call security associations. They'll call them crypto maps. But at the end of the day, with a policy-based VPN, which is what this is, you end up with a series of policies. If you have 3 subnets on your side that you want to talk to 3 subnet specifications on their side, you're going to end up with 9 pairs. That's just the way that it works. So you would end up saying new tunnel, and then you keep adding pairs that represent what you're offering mapped against what they're asking for. A couple other things. It's a command line tool for doing things via command line instead of via the web UI. The command line documentation also shows this is a RESTful, what's called a RESTful API. So it shows you both the command line functions, and in this case, this is showing you the RESTful invocation that you would do to define a new remote endpoint. So it's actually, you know, what you can see if you look through the API guide, you can see that it's a very controlled and very measurable number of commands that web user interface is using. Here's the RESTful statement using curl showing how you create a tunnel. Again, it gives you some insight kind of in how the device is working. Common sort of troubleshooting situations. One of the first things is no negotiation. What would happen is you would go to the network sniffer, and in this case, when I said source of the guy I'm connecting to or destination of the guy I'm connecting to, I'm seeing all this sort of network negotiation traffic. It's all going over, remember we talked about it goes over port 500. So this was us basically saying, hey, here's who I am. Who are you? You know, do we agree on who I think I am and who I think you are? And they basically said, yep, we agree. And then because we configured for NAT-Traversal, they switched over to 4500. So if you we saw nothing. It's probably a firewall problem on your side, on the VPC, because what that means is nothing's leaving. If we're putting out idents and we're getting nothing back, so if you see this in the log, again, it just repeats, initiating main mode, initiating main mode, initiating main mode. What happens is we're not getting any response back from the other side. So you're hitting, you know, box A at their site and they've configured it on box B, so there's no response because you're hitting the wrong box. Most often is their network ACLs are not allowing the UDP 500 and in this case UDP 4500 traffic from your VNS Cube's public IP. Also, same sort of thing, you know, it could be that your security groups are not letting the traffic out, so they're not getting a chance to respond, or again, their ACL is wrong. Phase 1 failures. Most often, it'll be pretty obvious if the pre-shared key is wrong. And again, there's 2 places to see the log, and right, I talked about this. So if I go to IPsec and EBGP, this is the monster log. But this is the log of everything going on inside that VNS cubed, right? And it fills up your browser. It starts at the oldest date and it works its way forward. So it's really a case of the best thing to do would be to download it and then look at it using an offline tool rather than going in the browser. But when you have a connection that's at least put together, you go to one of the tunnels and you say show logs. So in this troubleshooting guide, when I'm saying you see XYZ in the log, you're seeing this information in this section, the above the line section. And you're probably seeing very little going on if there's a problem in the live runtime information. So it's via the show log function here is what I'm talking about. So when the log says probable authentication failure, mismatch of pre-shared secrets, question mark, that is just, it's not always that obvious. There are things where the PSKs mismatch. I think we'll see a different error right after this. But basically what's going to happen is it's going to be a copy paste brought in invisible characters more often than not. We see that a lot, and your partner will swear. They'll say, no, I put it in 10 times. And you have to get them to fess up that they're like copying it out of an HTML based thing or a Word document where you picked up an invisible character. So then the log says for phase 1, it says no proposal chosen. You're mismatching on one or all of the phase 1 parameters, algorithm, hash, and Diffie Hellman group. There's two things to do there. If you'd gone in and put explicit phase 1 in the params box and it's not working, then what that means is they don't understand how policies are proposed by their device. Most boxes you connect to do not have specific parameters for a connection. What they have is a hierarchy of preferred, what they call policies. And when they make a connection, they just send over their highest policy. So a lot of times what they're using for phase 1 is not visible necessarily in the section of the box that they're configuring, and they don't necessarily know, or they have to go look, or they misread. We take whatever is their highest priority, meaning the thing that they offer first. The best way for us to do it is to match to that. So what you could do is you could remove then the phase 1 equals from the extra params box and see if VNS cubed will just match, right? Because then we'll sort of try and match to anything they're sending if they're not sending what we thought they were. So again, it could be one or all that they're off. So if we go look at our example host here, edit remote endpoint, and we make our params box a little bigger. If they had said AES 128 SHA-1 DH5 will probably mismatch, even though we got the SHA-1 DH5 right. You know, when you first start working with this, you go, well, why doesn't the log just tell me what the other guy's doing? Well, if you'd left the device open to, the firewall open, potentially a hacker could be trying to probe and see what things you accept and what you don't. So the logs don't necessarily, make it clear. What you would like is you'd like the other side to say, hey, dude, I'm saying, AES 128 MD5 DH2. But that is kind of a security risk. So they just tell you, we didn't match. So this is another log message where what's most likely going on is that you didn't match on the phase 1 parameters again. So there's sort of two different log messages here. So the next one is invalid ID information. So what this is a case of where they're wanting, either you need to specify their IKE Peer ID in that extra box, or they didn't enter your remote peer ID. So right here, if the remote endpoint is not directly connected to the internet, please enter its private IP address. This is often referred to as IKE ID or Peer ID, right? So this is the other guy on the other side what he has. So if you're getting an invalid ID message, it'll tend to be obvious based on the addresses in that error message that either you need to put an entry in this box or he has a box that he has to put in this entry. And you'll be able to tell that by the addresses that you see in the log. So phase one success, we saw this. So if we go back to our tunnel, we'll see SA established. So when you're dealing with Cisco people, they'll talk about security associations, and they'll often talk about phase one security association, SA, they'll abbreviate, or phase two security associations. So this is what you're aiming for, and that's what we saw here when we go to our tunnel homepage and we do our show log. That's the information that we received. IPsec SA established, and before that we saw Isaac Camp, or phase one SA established, phase two SA established. And again, that information, that's the raw information. You obviously see the same information in a more structured way here. Phase two failure is similar. The no proposal chosen is going to be a number of things. So we see that we had the phase one negotiation was successful, but then we immediately get a delete SA. So this is, we matched, we attempted to do phase two, and the other side says delete your phase one. More often than not, that means that there was a failure getting phase two to agree. So we'll see that. If you see the delete SAs, it usually means that the phase two couldn't agree. If you see the no proposal chosen repeating over and over and over again, but they're not sending the delete SA, they're not deleting the phase one and starting over, and if it's a Cisco ASA, what that means, and then we've seen this, I think, with Barracuda as well, where you're getting your phase one is kept, but your phase two is saying no proposal chosen, no proposal chosen. It still could be a mismatch, but it also, most often, if it's a Cisco ASA, they just have to send any traffic from their side. Cisco has the concept of interesting traffic, quote unquote. And what that means is traffic bound from their network to your side of the tunnel. Cisco won't complete a connection to a non-Cisco device unless there's traffic moving over the tunnel. So you need them to do a ping, anything to sort of light up the tunnel on their side, and then you get your synchronization in place, and then via the rekeys over time, then you're able to keep that connection going. So just in more detail, no proposal chosen, though, is for phase two is broader, right? You might have mismatched on the algorithm and hash. You might have a mismatch on PFS and Diffie-Hellman group. You might have a mismatch on what you're requesting versus what you're offering, so your tunnel specification. You know, again, to go back, if you on your side have 192, 168, 203, 24 is what I'm offering, and what I'm asking for is 172, 31, 103, 024, and what they put on their side was that they were offering their 024, but they were looking for 192, 168, 203/22, right? So just a wider range. If the policies don't match exactly, you will have a problem. When it comes to the phase two no proposal chosen, there's just going to be more work to do because you get effectively the same error message, whether it's a mismatch of your phase two algorithm and hash, whether it's a mismatch of the subnets, or it's a Cisco that won't complete the tunnel until you effectively it sends some traffic your way. Sometimes what you will see, you get the phase one established. You're not getting any deletes of the phase one, but you're getting invalid ID information, we tend to see that that's a mismatched subnets. It's implementation dependent based on who we're talking to, what kind of error messages people will send across. And then we showed phase 2 success, and we saw that in our connection. And what you'll see, and we'll talk about this, and it'll be one of the last troubleshooting items, is what you'll see here is NAT-D. This is NAT-Traversal. You see that NAT-Traversal is on by there being an IP address here in the log. It's possible for one side to think it's doing NAT-Traversal and the other side thinking not. And so you'll have a successful connection, but traffic won't pass because one of you is sending on UDP 4500 because you think NAT-Traversal is on, and the other guy is listening and sending on protocol 50 because he thinks it's off. You get the success message and you're all excited, right? But if you hit refresh in the log or you hit refresh on the tunnel homepage, phase 2 lifetime is 27.054 seconds right now. The last time we refreshed this page, 26.659. So we're counting down nicely. What you'll see is you'll see something like 100 seconds or 300 seconds here, and if you sit hitting refresh, it'll count down maybe for 10 or 12 seconds, and then it's back to 300 seconds. So we call that flapping, that the tunnel is flapping. It's connecting and reconnecting and reconnecting. When it's flapping, what is happening is more often than not, your phase 1 or phase 2 lifetime settings mismatch. And it could be either, or phase 1 and phase 2 lifetimes are identical on your connecting partner side, and they've convinced you to say phase 1 lifetime equals 3600S, and they've convinced you to put phase 2 lifetime equals 3600S, and it just causes communication and synchronization problems. But that's almost always the underlying problem. Here's a little more detail. So the tunnel's down, flapping. Sometimes it is because there's packet loss on the intervening route. So that's something that, if you've worked and worked and worked and you've matched up the lifetimes and you've had the conversation 5 different times with your partner, that you need to, that they have to match. Cloud segment they're connecting to is, US East, and they're coming from Singapore. It could be that there's just too much packet loss on the intervening internet route. And then we'd have to try and figure out effectively another way to get to them. I mentioned we got success, but nothing's passing. And so that'll be a case of where, for example, you think that, in your configuration, you've got NAT-T on, but when you look at the success statement, it says NAT-T none. Basically what that means is we offered up NAT-T, the other side said, nope, I won't do it, and we went ahead and connected, but now we're in this unclear state because we want to use UDP 4500, and they want to use protocol 50. So if you've got a successful connection, everything looks great, but nothing's passing, and it's NAT-T, you want to make sure that your log says NAT-T's on. If it's native IPsec, you want to make sure that your log says NAT-T's off. Otherwise, you're just sort of sending the right data but out on the wrong network ports. Yeah, and this is just the inverse of each other. The next thing that can happen when you've got success, so we're talking about traffic problems. So one traffic problem is we think we have a tunnel, but we disagree really on NAT-T, so the traffic's not matching up. The other one is everything looks absolutely fine, but what happens is the overlay clients aren't getting any information. Well, what happens is the overlay clients, we use TLS tunneling technology. We use the OpenVPN tunneling client. And so what happens is the overlay servers only receive routes when they connect. So when you create an IPsec tunnel or an IPsec tunnel comes up after the overlay server has connected, then what happens is those cloud overlay servers don't have the route. So even though the traffic's reaching them, they don't know what to do with it. So you would see that in the network sniffer, you would see traffic going to the cloud virtual IP address, but you wouldn't see any responses coming back. So what you need to do is restart the tunneling agent on the cloud server. We have a separate piece of software that runs on your cloud servers. That's the VNS3 routing agent. That's a very simple background service for Windows, a very simple background service for Linux boxes. That what it does is when a new route occurs inside the VNS3 network, the tunneling clients are able to pick up that route. Effectively, the routing agent can discover that there's a new route and install it on the local host, and that gets rid of the whole process of stopping and starting the OpenVPN service. So that's something that we would certainly encourage you guys to work with us, have your architects work with us, however you make deployment decisions to get the routing agent on your cloud servers. There is a possibility that there's a traffic problem because somebody tried to do something on the firewall. The VNS3 firewall, sometimes people have no rules in it, sometimes people have lots of rules in it. So it could be a case that somebody was trying to do some sort of natting or address translation because of the customer demand, and you ended up blocking the actual traffic. A couple gotchas. We've connected to just pretty much everything that moves out there. With Cisco ASAs, you will not get the tunnel to complete as a rule unless they're sending some traffic your way. Cisco, by default, has an idle connection timeout, which happens every 30 minutes, that there is no traffic over the tunnel. VNS3 has what we call the ping host. In order to keep that Cisco box from timing out, what you potentially do is you say, well, you know what, let's send and I know that there's a pingable host on their network of that address. I put in a ping host and I say, basically, this is seconds ping interval. Every 30 seconds, send a ping down the tunnel. And so then that keeps the Cisco timeout from kicking in. Ideally, you get the partner to set the Cisco idle connection timeout to 0, which means just keep connections open forever unless they're explicitly closed. Cisco ASA 8.4, anything 8 with an 8.4 in it, there were just so many bugs in this that we cannot keep a connection to the device. As soon as they came out with 8.5, we were fine. Everything before 8.42, we were fine. But there was just so many bugs in this stretch here that we cannot keep a stable connection to that. Firebox Watchguard for sure is going to need our local private IP set as its remote peer ID. Checkpoint is one of the biggest network vendors in the world. Checkpoint does not follow NAT-Traversal standards. There's like 18 drafts and 1 finalized standard for NAT-T. Checkpoint does not follow it, so you have to use native IPsec Protocol 50. And then one of the reasons we recommend the checklist is the first thing on the checklist is what's the make, model, and software revision, right? So Cisco 1941 iOS router 15.4 TM. Well, we know that as soon as we see that, we know we can help you. We know that software revision of Cisco was end of life in 2012. So we know we're going to be dealing with some age against the standards issues there, and then we can try and help. At the end of the day, really, just your resource is this page, and these videos have just been updated for basic configuration. So give those a look.